How many 3-digit positive integers, a, b, c, are there whose non-zero digits a, b, and c satisfy this equation? Where the... Okay, so we have a 3-digit number, a, b, c, and the equation given here that repeated infinitely is 1/3 with a repeated infinitely plus b repeated infinitely plus c repeated infinitely. Okay. Maybe if I just set up what this repeated decimal notation actually means in terms of infinite sums of powers of 10, maybe we can just solve for which values of a, b, c work, or at least, you know, count the combinations of a, b, and c that work. So I have reduced it down to this equation that a, b, and c have to satisfy, and a, b, and c themselves are, of course, positive integers between 0 and 9. Oh, so we're told they're all non-zero, so they're between 1 and 9. But I don't really see an efficient way of counting all of the solutions. I don't know for sure if this is even necessarily the best way of going through this problem. Well, certainly if a, b, and c are all equal to 1, that'll work, right? In fact, if a, b, and c are all equal, that'll work. Maybe is that the only way that this can work? Maybe, I mean, so if a, b, and c are equal, then just by looking at the thing we're trying to prove originally, it's clear that those will be equal on the right and the left. And if a, b, and c are equal, then we can cancel a, b, and c from all these. Do we get, so this will be 2, 9, 9, 7 equals, yeah, so the right-hand side, 999 times 3 will give us that. So is it possible then that we could just show that there's no case where a, b, and c are non-equal that works? I mean, I would almost be inclined to just guess that that is correct. I'm not super confident, but 9 is one of the available multiple choice options. But is it a trap? I'm sort of half confident that the answer here would be 9. I don't see a direct way. I don't see a simple way of arguing that. I'm sure you could work it out by looking at, like, you know, start with a combination that works where a, b, and c are all equal. And then, you know, if c changes by some amount, then look at what the change on the left and right hand side of this equation are, and show that you can't compensate for that difference. Well, hold on. What if I write everything on one hand side of the equation? Well, this is going to be kind of messy. I'm still not immediately clear what kind of argument I could make from this equation that a, b, and c have to be equal. Yeah, I mean, I'm gonna leave this one for now. I'm sort of half confident that the answer is 9 here, but I wouldn't put my life on it. Problem 17 is the first time that I submitted a solution without being fully confident in it. Even though I had some incorrect answers earlier in the test, I was confident when I submitted them. But problem 17, I thought it was quite reasonable, the answer that I was submitting, although I hadn't properly shown that that was the right answer, obviously, because it's not. And in fact, I haven't read the full solution to this question, and I'm not even sure what the correct argument is to get the right answer. It might be something that I just try and play around with and figure out on my own sometime. Let's take a look at the next one. Let tk be the transformation of the coordinate plane that first rotates the plane k degrees counterclockwise around the origin and then reflects the plane across the y-axis. What is the least positive integer n such that performing the sequence of transformations t1, t2, t3, and so on up to tn returns the point 1, 0 back to itself? So my first inclination here is to just write down what the matrix tk is and see if, I mean, I guess there's going to be some, we'll need some trig identities or something like that. Would that be a smart way of doing it, writing this matrix out? Because then we'll have to multiply a whole bunch of matrices together. Or is there an argument we could make? Could we just write out the sequence of points when operated on 1, 0? Right, so I think I've finally figured out the pattern going on here. The point, applying the transform, applying T1 and then T2 is like rotating -1 degree. And then when you subsequently apply T3, then T4, you rotate another -1 degree. So if you want to, every 2 transformations you apply, you move clockwise 1 degree. So to get all the way around 360 degrees, you've got to apply 720 of the transformations. So, and that's one of the given multiple choice answers. So I think that's it. Yeah, that took quite a bit longer than I expected. These problems are starting to get difficult. These are for 15-year-olds. So you should be proud of yourself if you do well on a contest like this. Problem 18, I also got incorrect. And this is a question that as soon as I saw the correct answer, I instantly knew what I had done wrong in my solution. I think maybe I was just mentally exhausted by this point. I'd been working on this for a couple of hours and just didn't really consider one particular case which gives you the solution to this problem. And by missing that case, I ended up doubling almost the numerical answer, which is correct. So Problem 18 is the last one in the test that I submitted a solution for and got incorrect. All right, let's check out the next one. Define ln as the least common multiple of all the integers from 1 to n inclusive. There is a unique integer h such that the sum of reciprocals up to 17 is equal to h over L17. What is the remainder when h is divided by 17? What is the remainder when h is divided by 17? So there's got to be, there's probably a clever way to figure this out rather than just simplifying everything on the left-hand side. Can we figure out what this least common multiple of all numbers up to 17 is? Well, 17 is prime. That might help. What's 17 times 16? Well, I guess it'll just be the product of this least common multiple will be the product of the primes less than 17. We may have to account for other things, or maybe we could just like multiply through by L17 and then we get h I'm just going to play around with this and see if something nice comes up. Okay, so after a whole bunch of algebra, factors, blah, 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 I end up with 5. And that is one of the multiple choice answers. Unless I've made some arithmetic mistakes, or if I counted all of the necessary prime factors to get the least common multiple of all these numbers, I'm pretty confident in this, that the answer is 5. So yeah, I'm going to stick with that. Let's check out our next one. A 4-term sequence is formed by adding each term of a 4-term arithmetic sequence of positive integers to the corresponding term of a 4-term geometric sequence of positive integers. Okay, the first 3 terms of the resulting 4-term sequence are 57, 60, and 91. What is the 4th term? Okay, so we start with 2 sequences, an arithmetic and a geometric. We add them together, and it gives us the first 3 terms. So, and we want the 4th term. So there's three parameters involved here that we can solve for, right? There's 4, or are there 4 parameters? Okay, well the first sequence is going to be A plus D, A plus 2D, and A plus 3D. That's the arithmetic sequence. The geometric sequence is n, Rn, r squared n, and r cubed n. We add these together to get the first 3 terms of the resulting 4-term sequence. Okay, so A plus n is 57. A plus D plus Rn is equal to 60. A plus 2D plus r squared n is equal to 91. And we're asked for the sum of those. So maybe we won't be able to solve for everything here, but with some clever manipulations, we might end up with the sum of those. So let's see what we could possibly do here. And we're told that all of these numbers all of these numbers are integers. R is not necessarily an integer, but these four numbers are integers. Positive. All right, after a whole bunch of algebra, a little mistake, and finally getting something, I arrive at the answer of 206, which is one of the four options available in multiple choice. So I'm pretty confident in this one. Yeah, it just came down to, writing down the terms of each of the sequences and the sums and computing some differences. Eventually, you're able to solve for all the coefficients. All right, let's take a look at the next one. These problems are getting kind of difficult, but I'm pretty driven to finish this, so let's see what happens. Oh my goodness. A bowl is formed by attaching four regular hexagons of side 1 to a square of side 1. The edges of the adjacent hexagons coincide as shown in the figure. What is the area of the octagon obtained by joining the top 8 vertices of the 4 hexagons situated on the rim of the bowl? Okay, this is a pretty complicated diagram. I don't know if I'll be able to draw this exactly, but you take a square. Maybe you can draw a figure as it would look from above. You take a square. To each of these squares, you add a hexagon, a regular hexagon. So imagine I glue hexagons like this to each side of the square, all four of them, and then you fold these hexagons up until they touch so that this side will be glued to this side. And then, so you have 4 hexagon edges that are sort of up high. And then you imagine you connect all of those around to form an octagon, and it's asking for the area of that octagon. Sheesh. So it's a regular octagon. If we can figure out, wait a minute, is it a regular octagon? Probably not. This would be too easy if it were, because then we know the side length. My first, one possible way of doing this. What do we need? Okay, so as seen from above, we have an octagon. But the side lengths are not all equal. These 4 side lengths are all equal to 1, and they correspond to the edges of the hexagon that are glued to the square. But these side lengths, they're all equal, won't be equal to, the lengths won't be equal to 1. And our original square is kind of down here. This is kind of like the shape we would see if we projected the bowl figure into the plane, or if we're looking at it straight down. So it's kind of weird, but that is intended to be a regular hexagon. It's just been rotated up, which is why. Okay, anyway. So this line segment eventually will come from joining that point to that point. So one way that we could find its length is by writing these 2 points, the coordinates of those points. They're both going to undergo rotations, so we can figure out their new position, and then we can compute the distance between them. What is the rotation that these hexagons have to go under until their edges coincide? Okay, I'm gonna start working out some of the geometry and some of the rotations and positions and whatnot, and see if I can solve for this angle of rotation. All right, this is unfortunate because I've gotten to an answer which is not one of the multiple choice options. So I'm not sure exactly what I did incorrectly here. I mean, I think that's the right ratios for this triangle. Could be wrong about that. Are these backwards? Does this change the answer? So not only did I have that backwards, but I forgot about this factor of 2. So let's do this properly. So x should be, is x just 1? No. Okay. So what do I get here? Area is 1 plus 4 plus 2, which is 7. And that's one of the options in the multiple choice. Somewhat confident in this answer now, especially given that it's one of the 4 multiple choice options. Let's keep going. Let's take a look at the next one. Suppose that 13 cards numbered 1 to 13 are arranged in a row. The task is to pick them up in numerically increasing order, working repeatedly from left to right. In the example below, cards 1, 2, 3 are picked up on the first pass, 4 and 5 on the second pass, 6 on the third. Okay. Oh my goodness. So we have a crazy combinatorial problem. The idea is you loop around the cards from left to right and you pick them up in order. For how many of the 13 possible orderings of the cards, of the 13 factorial possible orderings of the cards, will the 13 cards be picked up in exactly 2 passes? All right, actually, I guess I can think about how what we want to do is construct an ordering of the cards such that you can pick them up in 2 passes. The first thing we do is, of the 13 cards, we're going to break them up into two groups. And there are 12 ways of doing that, right? There's 12 ways where we can divide the 13 cards in half, right? There's 12 gaps between them. And then when we're given two collections of cards, we need to compute how many ways we can sort of interlace these. I know there's a formula for that as well. I don't remember what it is. So we've got 8, 1, 7, 8, which is one of the options. Hey. 8, 1, 7, 8. Cool. Yeah, my brain is getting a little fried here, but I want to keep going. Number 23. Isosceles trapezoid, ABCD, has parallel sides AD and BC, with BC smaller than AD, AB equals CD. Let's draw out what we've just said. There's a point P in the plane such that PA equals 1, PB equals 2, PC equals 3, and PD equals 4. Goodness. So a point in the plane I wonder if it could possibly be inside this trapezoid. These geometry problems are really hard. I feel like if you're someone who's getting really into math contests, there's a lot of formulas that are nice to have in your back pocket for these geometry problems, but it's just not something I have experience with. So the point doesn't necessarily have to be in the trapezoid, right? We don't know that for sure. Would it make sense to write out a whole bunch of distance formulas and hope that things will work? I don't even know where to start on this one. That's a cool feeling. I think this is like another one that I might just try and come back to. I'm going to skip it for now. How many strings of length 5 formed from the digits 0, 1, 2, 3, 4 are there such that for each j in 1, 2, 3, 4, at least j of the digits are less than j? Oh, good God. For example, 0, 2, 2, 1, 4 satisfies the condition because it contains at least one digit less than 1, at least 2 digits less than 2, at least 3 less than 3, at least 4 less than 4. Okay, this might not be as bad as it sounds originally. Okay, so I feel like maybe there should be a way to parameterize, like, if I tell you how many times each digit occurs, then you find out how many permutations of those digits there are, and then sum over the number of allowable collections of the digits. I think this is another one to come back to. And when I say come back, I'm starting to realize that I'm going to break my promise and probably just not come back. Let R, S, and T be squares that have vertices at lattice points in the coordinate plane, together with their interiors. The bottom edge of each square is on the x-axis. The left edge of R and the right edge of S are on the y-axis. And R contains 9/4 as many lattice points as does S. Top two vertices of T are in R union S, and T contains 1/4 of the lattice points contained in R union S. So there's a figure not drawn to scale. I'll reproduce something like that here. So that's square R, S, and T. And right, it tells us the ratio of points contained in them in some various ways. The fraction of lattice points in S that are in S intersect T is 27 times the fraction of lattice points in R that are in R intersect T. What is the minimum possible value of the edge length of R plus the edge length of S plus the edge length of T? Okay, well, first of all, let's realize that R and S are parameterized by single positive integers. So R, let's let this is going to be, okay, lowercase r is the side length of R. Lowercase s is the side length of rectangle S. T has two integers parameterizing it. Let's say T1, why don't we just label it? That's T1, and that's T2. So this x coordinate here is negative T1, and this coordinate is T2. So T1 we're implying to be a positive integer. Okay, so I'd like to start to translate some of the statements about the number of points they contain into equations. Yeah, this is actually kind of an interesting one. I know I've said that others I'll come back to. I was probably lying. I doubt I will. But this one, I might just try and work on my own for fun someday. And if I get it, then this one might be a good one to do like an outline on. So now that I've finished my attempt at the AMC 10, I thought it would be nice to summarize my performance, give some final thoughts, and talk about my experience in doing the whole thing. So in terms of my performance, I had 14 correct answers, 5 incorrect answers, and there were 6 problems where I didn't really commit any answer or didn't get a solution. In terms of what I might change to improve my performance, the first thing for sure would be to be a little bit more careful in some of my solutions. Of the 5 incorrect answers that I submitted, there were 3 that boiled down to very stupid mistakes, oversights of very basic things, and I think there's quite a big difference between submitting 14 correct answers versus submitting 17 or maybe even 18. Of the incorrect answers I got, there was only one where, as I was doing it, I really wasn't very confident in the solution. Specifically, that's for problem number 17. So in my commentary at the end of question number 17, I actually say that. It's the only question where I submitted an answer where I wasn't actually fully confident in the answer, and for some reason I submitted it anyways. In terms of other things that I would do if I were ever to write this contest for real, time management would be huge. You only have 75 minutes to answer these 25 questions. I took a lot longer than that, and I purposely was not keeping track of time because I wanted to be able to express my thoughts out loud on each question. If in writing the test for real, of course, you're not going to be expressing your thoughts out loud. You don't have to worry about clarity of your thoughts to an audience. You can kind of get right down to work right away. But if I were limited to 75 minutes, my strategy on a test like this would be to read a question. If I know how to answer it immediately, then answer it. If I don't know immediately the approach I would take, I would skip it and go to the next question. Because of the 25 questions in the test, chances are you're going to be able to fill up that 75 minutes with questions that you know how to answer immediately. So there's no point wasting time on questions that you don't really know how to approach right away. And the last thing that I would do differently, if you're really serious about this stuff, there's definitely some preparation that you can do. If you ended up watching or at least sort of glancing at my solutions to all 25 of these questions, there's a little bit of a common theme on the ones that I got stuck on. Anything to do with geometry, so really complicated diagrams with triangles and circles and all that kind of stuff, quadrilaterals. I wasted a lot of time sometimes just walking in circles on those. And other ones that I probably spent more time on than usual would be things that are combinatorial or discrete mathematics. Those are just things that are outside of my comfort zone in general. Now, if I wanted to prepare myself to perform well on a contest like this, I would review those types of subjects in preparation, give myself several weeks or a month or something like that to really dive deep into those types of problems. I mentioned a few times on these geometry problems that there's a whole bunch of identities that have to do with triangles and circles and side lengths and angles and all that kind of stuff. I just have no idea what those formulas are. I could probably derive them given enough time, but there's no way you're going to do that in the middle of a contest. So having access to those formulas might have made some of those questions immediately obvious. So those are my thoughts. One of the best ways to prepare for a contest like this is to practice on a previous contest. As I mentioned a few times going through my attempt, the questions ramped up in difficulty a lot faster than I expected. So having an idea of what type of level of difficulty the questions would be before going in would be really nice. I think what I'm going to do in the future with some of this contest stuff, I'm going to mix it up between writing them rules as written, so actually timing myself and using the strategy that I've just outlined on time management and trying to be more careful, and then evaluating my performance, but also still doing some where I'm not keeping track of time. That way I can really give commentary as I'm going. Let me know what you think about these contests. If there are specific contests that you want me to attempt, you can get in touch, leave a comment, or send an email. Otherwise, thanks for watching.